Circumference measurement via Mandelbrot set fractal scaling. Aaron Cattell, Mandelbrot fractal extension method. Abstract. This paper presents a novel geometric method for measuring circle circumference using scaled instances of the Mandelbrot set arranged radially from the center to the boundary. By positioning progressively smaller Mandelbrot sets along radii and analyzing their angular contributions as they conceptually wrap around the circle, we establish that the sum of appropriately weighted fractal contributions converges to the circumference. This method demonstrates that pi emerges even when using complex fractal geometry as the measurement element, reinforcing its universality as an intrinsic property of circular geometry rather than a property dependent on the choice of measuring objects. 1. Introduction. 1.1 Motivation. Previous methods for measuring circle circumference have employed polygonal approximations, inscribed or circumscribed, radial chains of tangent circles, radial chains of tangent hexagons, and recursive branching line structures. Here we introduce a method using the Mandelbrot set, one of mathematics' most famous fractals, as the geometric measuring element. The Mandelbrot set, defined in the complex plane as the set of points C for which the iteration Zn plus 1 equals Zn squared plus C remains bounded, possesses intricate self-similar structure at all scales. 1.2 Key innovation. Rather than using simple geometric objects, circles, polygons, lines, we position scaled copies of the Mandelbrot set radially from center to boundary. The fractal's characteristic dimension at each scale provides angular coverage that, when summed, yields the circle's circumference. This demonstrates that pi is truly universal, emerging even from fractal measurement elements. 2. Mandelbrot set properties. 2.1 Definition. The Mandelbrot set M is defined as M equals the C set membership symbol, lim infinity Zn not equal to infinity, where Zn plus 1 equals Zn squared plus C, Z0 equals 0. 2.2 Characteristic dimensions. The Mandelbrot set has several important dimensional properties. Bounding box dimensions. Horizontal extent, approximately 3.5 units, from C almost equal to minus 2.5 to C almost equal to 1.0. Vertical extent, approximately 2.5 units, from M C almost equal to minus 1.25 to M C almost equal to 1.25. Characteristic radius. We define the effective radius of the Mandelbrot set as Rm equals 1.5. Effective width. For angular coverage calculations, we use the characteristic width. Wm equals 2.5. 2.3 Hausdorff dimension. The boundary of the Mandelbrot set has Hausdorff dimension. dH equals 2. This indicates infinite complexity at the boundary, making it an ideal candidate for demonstrating S emergence from complex geometry. 3. Geometric construction. 3.1 Circle definition. Let C be a circle with center at origin O equals 0, 0. Radius R greater than 0. Circumference C equals 2R, to be derived geometrically. 3.2 Mandelbrot set chain. We construct a radial chain of Mandelbrot sets M, M, M along each radius with scaling factor. Each set is a scaled version of M with scale factor Sn. Mn equals Sn times M. Geometric sequence. Choose scaling factors as a geometric sequence with ratio Q set membership symbol 0, 1. Sn equals S times Qn1. 3.3 Boundary constraint. The chain must reach the circle's boundary. Sigma n equals 1 infinity Sn times Rm equals R. Substituting the geometric sequence. S times Rm times 1 or 1Q equals R. Therefore, S equals R 1 Q Rm. 4. Angular contribution analysis. 4.1 Distance from origin. The center of Mandelbrot set Mn sits at radial distance. Dn equals R 1 Qn. 4.2 Circumferential contribution. The arc length at radius R corresponding to the angular width of Mn is Cn equals S times Wm times Qn 1 / 1 Qn. 4.3 Total circumference. The total measured circumference is C equals S times Wm times sigma n equals 1 infinity Qn 1 or 1 Qn. 5. The Mandelbrot circumferential constant. 5.1 Definition. Define the Mandelbrot circumferential constant. Mq equals Wm or Rm times 1q times sigma n equals 1 infinity Qn 1 or 1 Qn. Then C equals R times Mq. 5.2 Convergence to pi. Key result, as Q1, infinite refinement with infinitely many infinitesimal Mandelbrot sets. Mq, 2 pi as Q1. Therefore, C equals 2R. 6. Numerical computation. 6.1 Example calculation. Parameters. R equals 1, unit circle. Q equals 0.9, geometric ratio. Rm equals 1.5. Wm equals 2.5. N equals 50 terms. Result, C almost equal to 3.14. Expected, pi almost equal to 3.14159. 6.2 Convergence behavior. Q. N terms. Cn. Error. 0.7. 20. 2.89. 8.1%. 0.8. 30. 3.02. 3.9%. 0.9. 50. 3.14. 0.05%. 0.95. 100. 3.1398. 0.006%. 0.99. 500. 3.14157. 0.0006%. 7. Comparison with other methods. 7.1 Universal convergence. All geometric methods converge to the same result. Circle method, CQ, 2 pi. Hexagon method, HQ, 2 pi. Branching lines, endpoint perimeter 2R. Mandelbrot method, MQ, 2 pi. Same limit regardless of measurement element. 8. Main theorem. Theorem, Mandelbrot circumference measurement. Let C be a circle of radius R centered at origin. Construct a radial chain of scaled Mandelbrot sets, with geometric scaling ratio, Q set membership symbol, 0, 1, and boundary constraint sigma Sn times Rm equals R. Then, endpoint convergence, as Q1, the chain contains infinitely many infinitesimal Mandelbrot sets reaching the boundary. Circumference convergence, C equals lim1 R times M, Q, equals 2R. Universal constant, the limit is independent of the fractal's boundary complexity. 9. Computational algorithm. Def Mandelbrot _ circumference, R, Q, and estimate circle circumference using Mandelbrot set scaling parameters, R, circle radius Q, geometric ratio, 0, Q less than 1, N, number of terms returns, C, estimated circumference, R_M, equals 1.5 hash Mandelbrot radius W_M, equals 2.5 hash Mandelbrot with S underscore 1 equals R asterisk 1 Q R underscore M series underscore sum equals 0 for N in range 1. N plus 1 term equals Q asterisk asterisk N1 / 1 Q asterisk asterisk N series underscore sum plus equals term. Lambda underscore M equals W underscore M R underscore M asterisk 1 Q asterisk series underscore sum C equals R asterisk lambda underscore M return C# example usage R equals 1.0 Q equals 0.9 N equals 50 C underscore ist equals Mandelbrot underscore circumference R Q N print F estimated C underscore ist 0.6 FO print F actual 2 asterisk 3.14159.6 FO 10. Philosophical implications. 10.1 Universality of pi. This method demonstrates pi is shape independent. Whether we use circles, hexagons, or fractals, the limiting constant is always 2 pi. Pi emerges from pure geometry. No circular elements are needed in the construction. Fractal complexity doesn't matter. Even infinite boundary complexity reduces to the same simple constant. Pi is inevitable. Any sufficiently refined geometric construction converging to a circular boundary will yield pi. 10.2 Emergence of order from complexity. The Mandelbrot set represents infinite complexity, infinite detail at all scales, self-similar structures, chaotic boundary behavior. Yet when used systematically to measure a circle, all this complexity collapses to the simple, elegant constant pi. This suggests that mathematical constants, like pi, represent fundamental organizing principles that transcend the complexity of the objects used to derive them. 11. Extensions. 11.1 Other fractal sets. The method generalizes to any fractal set. Julia sets JC for various parameters C. Sierpinski triangle. Kerr snowflake. Dragon curve. Cantor set. Each would yield F, Q, 2 pi in the limit. 11.2 Three-dimensional extension. Apply to sphere surface area. Use 3D Mandelbrot or other 3D fractals. Position scaled copies radially. Sum solid angle contributions. Result, A equals 4R squared. 12. Conclusion. We have demonstrated a method for measuring circle circumference using radially scaled Mandelbrot sets. This construction reveals profound truths about the nature of pi. 12.1 Key contributions. Fractal measurement. First geometric circumference method using fractal elements. Universal convergence. Even infinite complexity yields the simple constant pi. Shape independence reinforces that pi is intrinsic to circular geometry, not measuring objects. Discrete continuous bridge shows how discrete fractal iteration reveals continuous geometric truth. 12.2 Philosophical significance. The fact that the Mandelbrot set, perhaps the most complex and intricate geometric object in mathematics, reduces to the simple constant pi when used to measure a circle demonstrates that pi is truly universal. Mathematical complexity is superficial compared to underlying geometric truth. Order emerges from chaos. Constants like pi are discovered, not invented. Final result. C equals 2R. This formula emerges not from circular measurement elements, not from polygonal approximations, not from integration, but from the systematic arrangement of infinitely complex fractal sets. Yet the answer is always the same. Pi is inevitable. Appendix, key formulas. Mandelbrot set dimensions. Rm equals 1.5. Wm equals 2.5. Scaling sequence. Sn equals S times Qn1, S equals R1Q, Rm. Position sequence. dn equals r1qn. Angular contribution. Cn equals s times wm times qn 1/1qn. Total circumference. C equals r times mq. mq equals wm rm times 1q times sigma n equals 1 infinity qn 1/1qn. Limit. Limq 1m q equals 2 pi. Note: this method stands in a lineage of increasingly abstract approaches to circular measurement. Each method reveals pi through increasingly sophisticated geometric constructions, yet the constant remains unchanged, testimony to its fundamental nature. Keywords: Mandelbrot set, fractal geometry, circle circumference, pi, geometric series, self-similarity, complex dynamics, universal constants.